this audacious sounding idea that the laws of physics underlying everyday life are completely known. Now, when I say this, people like to stop listening when I say underlying everyday life, so I want to emphasize that. I'm not saying the laws of physics are completely known. I'm not also saying that everyday life is completely known. There's plenty of things about everyday life that I don't know about. Plenty of things about physics we don't know about. Dark matter, dark energy, black holes, the Big Bang. Plenty of physics that is not about the underlying laws that we don't know. High temperature superconductivity, turbulence, and so forth. I'm making quite a specific claim that you and I, and all the stuff right in front of us, literally the stuff we can touch and see in our everyday lives, these are made of things. Atoms, electrons, protons, neutrons. Those protons and neutrons are made of quarks. And all these particles interact in a certain way, and we know both what those particles are, and when I say we know, not only do we have a good idea, but 1,000 years from now or 1,000,000 years from now, this idea will still be right. Hopefully we will learn more. I mean, maybe the quarks and electrons and so forth are made of even tinier things. That's great. But there won't stop being quarks and electrons, and we won't be wrong about how they interact. There are deep reasons for believing this is true. Let me just tell you what the ingredients are. This is an atom, right? This is a neutron and a proton and electron, so it's a deuterium isotope of hydrogen. The electron is held together to the nucleus by electromagnetism. The individual protons and neutrons are made of quarks, up and down quarks, which are held together with a strong nuclear force. Occasionally, an up quark or a down quark can convert into the other one via the weak nuclear force and give off a neutrino in the process. Everything is pulled toward everything else by gravity, and everything swims in the background of the Higgs field. The Higgs boson particle is something we discovered just in 2012 with the Large Hadron Collider. The particle is what happens when you start this field vibrating, but the field itself, the Higgs field, pervades all of space, affects the properties of the other particles that we're made of. There are more particles than this. These matter particles, the electron, the quarks, and neutrinos, they all have heavier cousins, but they decay away very, very quickly if you try to make them. They do not affect our everyday lives. We know them and we can complete them into theory, but you don't actually need to know them to know what you and I are made out of. So that's it. As far as our everyday world is concerned, the point is that there is no new particle, no new field, no new force that we will ever discover that will have an impact on our literal everyday biology or environment, like what holds this table up. We hope to discover a lot more physics. It will not affect you or what you're made out of.
We humans, alongside everything else on Earth and everything we have ever discovered in space, compose less than 5% of the universe. This type of matter, also known as ordinary matter, is minuscule compared to dark matter and dark energy, which together comprise the remaining 95% of the universe. However, that fact shouldn't suggest we are ignorant of what constitutes ordinary matter and how it works. In classical physics and general chemistry, matter is any substance that has mass and takes up space by having volume. All everyday objects that can be touched are ultimately composed of atoms. But where do the atoms that make us up come from? While most of the cells in our body regenerate every 7 to 15 years, many of these particles that make up those cells have actually existed for billions of years. The hydrogen atoms in us were produced by the Big Bang, while heavier elements such as the carbon, nitrogen, and oxygen atoms were made in the hot furnace of the burning stars. The very heavy elements in us come from exploding stars. Although it is mind-blowing to learn our atoms come from stars going supernova, there is still a mystery of how the collection of those atoms gives rise to something like consciousness. This is known as the hard problem of consciousness. It's the problem of explaining why and how we have qualia or phenomenal experiences. Another enigma is why our experience of the classical world differs so massively from quantum mechanics, if indeed we truly understand the framework of matter that makes us up.
So in terms of the particles that actually matter to you and me, that make us up, we know the complete collection. So the question is, the big question ahead of us today is, if that's true, why does the manifest world of our everyday experience seem so different than the underlying laws of quantum mechanics and quantum field theory and particle physics? And the answer is this tricky idea called emergence. you can have an underlying layer of microscopic fundamental physics made of particles, forces, and differential equations. It can do what Laplace said: information is conserved from moment to moment over time. The rules of physics are patterns written down in differential equations. And yet, when you collect together many of these particles, there can be collective behavior that is implicit but not at all obvious in this microscopic rules. This collective behavior could emerge into wholly new concepts and vocabularies. So the idea that there are tables and chairs and peoples and planets, that's nowhere obvious in this underlying description. But the two levels can be compatible with each other. This is the world of cause and effect, reasons why, dissipation, and most importantly, the arrow of time, the difference between past and future. So our task today is to see how this one level can be compatible with the other one. Why can we think that there are reasons why and causes and effects, and for that matter, right and wrong and truth and beauty in the world, even though at some level, deep down, it's just stuff happening according to that equation that I showed you.
A scientific concept, as well as a measurable physical property that is most commonly associated with a state of disorder, randomness, or uncertainty, is entropy. Ludwig Boltzmann explained entropy as the measure of the number of possible microscopic arrangements or states of individual atoms and molecules of a system that comply with the macroscopic condition of the system. A common misconception of entropy is the conflation with additional misunderstandings of the second law of thermodynamics, used by some people as the basis of unfounded arguments against evolutionary theory. Entropy is not disorder or chaos or complexity or progress towards states of objects in the universe. Entropy is simply a metric, a measure of the number of different ways that a set of objects can be arranged. Of course, the number of disordered arrangements of any given object far exceeds the number of ordered ones, hence the misconception.
The entropy of the universe increases monotonically through its history, but the complexity comes and goes. The universe became more and more complex up to the present day, and will start becoming less and less complex as those stars stop shining. The stars stopped shining about 1 quadrillion years after the Big Bang. So it's today, when gravity has pulled things together, made the universe lumpy, brought into existence planets and stars and galaxies, biospheres and people, that the universe is interesting and complex. As small as we are compared to the vastness of the cosmos, we live in the interesting part of the history of the universe for exactly that reason. And this kind of reasoning can help us explain even questions like why life itself exists.
Supernovae are violent stellar explosions prevalent throughout the cosmos. Studying them revealed the enigma of dark energy, a force that will determine the fate of the universe. This unknown form of energy that affects the universe on the largest scales came from observational evidence of exploding stars, which showed that the universe does not expand at a constant rate. Rather, the expansion of the universe is accelerating. The best current measurements indicate that dark energy contributes 68% of the total energy in the present-day observable universe. A hypothetical form of matter thought to account for approximately 85% of the total matter in the universe is dark matter. Its presence is implied in a variety of astrophysical observations, including gravitational effects that cannot be explained by accepted theories of gravity. For this reason, most experts think that dark matter is abundant in the universe and that it has had a strong influence on its structure and evolution. Dark matter is called dark because it does not appear to interact with the electromagnetic field, which means it does not absorb, reflect, or emit electromagnetic radiation, and is therefore difficult, if not impossible, for our current instruments to detect. As mentioned before, dark energy and dark matter comprise 95% of the universe, which means we still have a whole lot to learn about the deepest mysteries in cosmology. But we're thankful for the work of scientists that made it possible to confidently say, we understand 5% of the universe. Thanks for watching. Did you like this video? Then show your support by subscribing and ringing the bell to never miss videos like this.